Hi, Justin.
Good morning.
We'll get started in a moment. I already hit the recording button, so I wouldn't forget to do that. So just so everybody knows you're being recorded. Okay, I think we can get started. I just wanted to, before turning it over to the technical folks, start with a few kind of basic housekeeping items. For those who don't know me, my name's Laura Hart. I'm a water policy analyst with the department and the rulemaking coordinator on the groundwater allocation rulemaking effort. This meeting today, as well as the one scheduled for tomorrow, they're both designed to be technical information sessions. They're a follow-up to some material that Ben presented during our last RAC meeting on December 14th. Ben presented some information, and we also sent out a written memo sort of summarizing that information. It was material pertaining to the science underlying our proposed rule language for reasonably stable groundwater levels. And there was some interest among RAC members to have a follow-up session to ask more questions about that technical information. So today's meeting and the one scheduled for tomorrow at the same time, they're both narrowly focused on that material. The science underlying that definition of reasonably stable groundwater levels. And Justin will say a few additional clarifying points as well, but I just wanted to remind everybody that that's why we're here today. Justin, if you could admit people as I see them coming in, that'd be great. Okay, let me finish my little spiel here. RAC members were asked to submit questions ahead of time so Ben could kind of tailor his presentation to address any outstanding questions RAC members might have. And my understanding is Ben's done that, and so he's going to be as responsive as he possibly can to the questions that we received ahead of time. As he goes through the presentation, I'd like to ask everybody to this meeting is for the RAC members, so we will be only taking questions from RAC members, at least at the start, based on, the fact that we have a lot of people attending, and we want to be responsive to RAC concerns. So we ask that RAC members, as Ben goes through his presentation, please wait till he gets to the end of a slide before raising your hand if you've got a question or comment. And then if we don't see any for that slide, we'll just continue to move through the content. We do have a designated public comment period. I think I maybe messed up some of the materials. This meeting's supposed to be from 9 to 10:30. So we're going to pause at 10:15, and I'm going to ask if any members of the public have any questions or comments they wish to offer. Please limit your questions and comments to the materials presented today. We understand folks might have questions or comments about other aspects of our rulemaking effort. If you would like to submit comments concerning those other aspects of our rulemaking effort, you can submit them to me in an email, or you are welcome to join us at our next scheduled RAC meeting, which I believe is January 23rd. Is that Tuesday? Let me just make sure. Yeah, January 23rd from 8:30 to noon. It's hybrid. We have a designated public comment period at that meeting as well. So the public's always welcome to join and provide comments. A reminder, this meeting's being recorded and we'll post it within the next couple of days. I'll work with the webmaster folks to get them up online as quick as possible. So I'm going to turn it over to Justin to add anything else that you might want to clarify or explain, and then we'll turn it over to Ben. Thanks for joining us, everyone.
Yep, thanks everybody. I'm Justin Iverson. I manage the groundwater section here at the department, and I'm just going to reiterate a couple quick things because we see a good number of people here, which is great. I want to make sure that folks understand the background. So again, this is a follow-up to materials that were presented during RAC number 7 regarding reasonably stable water level definition. If folks here are interested in a more general discussion, I'd encourage you to go to our rulemaking website, which is linked right on our homepage under Hot Topics, I think, and review that RAC number 7 recording. This is intended to be a additional technical discussion and to provide opportunity for some RAC members that requested additional time for conversation about this technical underpinning. So just want to make sure everybody's oriented. We haven't drafted this presentation to be kind of generally at a real general level. So it's a very detailed level. And I'll reiterate one other thing, which is for RAC members, please interact as requested with Ben, and for other folks, please hold your comments till the public comment period. And with that, I'll turn it over to Ben.
Thanks, Justin. I'm going to share my screen now, hopefully, and turn it into a slideshow. If we can get the Zoom stuff to be less intrusive. There we go. How's that? Can everyone see?
That looks good. Oh,
presentation there?
Yeah, right. That's good right there.
I can see the anyone who's got, there we go. All right, great. So I'll try to pause momentarily after slides and check for hands, but Justin, please feel free to interrupt if I miss someone. Thank you everyone for attending. I really appreciate the attention from the RAC on our analysis of water levels in Oregon wells that we've been using as part of developing the proposed definition of reasonably stable groundwater levels. I also really want to appreciate all the RAC members who submitted questions in advance of this this technical info session. We had more than 30 questions and comments submitted late last week, and I have done my best in this presentation to address the major themes brought up in those questions. I haven't addressed every single question point by point, but I'm hoping that through my presentation we'll cover the vast majority of the content and clarify so that everyone understands what was done. At the same time, we've left some time at the end of the meeting. I guess here we go. Just a general idea. We've gone through the introductory part. Now I'll present the brief review of the methodology, including some slides that I developed to help answer some of the submitted questions. We'll then have time for questions with the RAC, and then in the last little bit, some time for public comment. So with that, let's jump right in. First, reviewing a slide that was presented in RAC 7. Many of the slides that I'm going to show were presented in RAC 7. I'm going to go pretty fast through ones like this that were already presented. I just think that this is useful context to load into our heads for the following discussion. The main point of this slide is that the proposed definition of reasonably stable groundwater levels balances a number of objectives that are sometimes in tension with each other. So especially, we might want the test to be both consistent in that it doesn't switch back and forth between reasonably stable and not, when that's not necessary, when a trained hydrogeologist would clearly indicate that it's either consistently declining or consistently stable. But at the same time, we want the test to be sensitive to declines when they are occurring in a consistent manner. And that trade-off is one of the ones that's significantly influenced by the analysis that was presented in the memo and that we're going to be reviewing today. Other of those objectives including limiting the burden of collecting additional water level data and making sure that the definition is transparent and easy to implement. The dynamically stable range is a concept that we are using to understand water level fluctuations and how those should relate to sustainable groundwater resources management. This memo is one way to quantify the dynamically stable range for water levels in Oregon, both in terms of the magnitude of water level changes, the height of that blue bar at the top, as well as in the proposed definition, we have a rate test, and we are including quantification of the rates observed in long-term stable records as part of defining what is dynamically stable for water levels in Oregon. I think perhaps the most important distinction that I want to highlight in this presentation that came through in the most comments and questions clarifies what is the goal of this analysis. That is, we are looking for characterizing the behavior of water levels in wells that is stable in the long run, rather than trying to identify and characterize behavior of water levels that are purely influenced only by precipitation, or in other words, are only natural. The goal here is not to characterize natural variability. And that's because that's a hard thing to do. It's, as many RAC members have pointed out, the causes of water level declines are sometimes many, influenced by multiple factors, and difficult to disentangle even for a trained hydrogeologist with a sophisticated model with which to interpret data. And that's not something that's going to be an option under the proposed definition of reasonably stable groundwater levels. We're proposing a relatively simple, objective set of criteria to distinguish reasonably stable or not, without trying to infer what is the cause of potential declines, but rather trying to answer this first question: do we expect water levels that have declined to then subsequently recover? In order to do that, we look at the data observed in wells around the state where water levels have been observed to fluctuate and are, in the long run, over the entire period of record of those wells, showing limited long-term declines. So it's understandable that RAC members and others found this to be an interesting question because the department has, in some of its previous communication, talked about natural variability. And even the fact that we are using precipitation as a way to identify these cycles, which are a significant source of variability that we do in fact want to capture as reasonably stable. We've realized in the process of doing this analysis that requiring water levels to be driven only by precipitation is not really feasible. It's not really necessary. It's not even really the right question. Many water levels that do show long-term stability, that is limited declines over the entire period of record, are influenced both by precipitation and by anthropogenic activities. During dry years or periods of years, oftentimes that triggers additional pumping, and that can cause water levels to decline farther than they would have without that pumping. And if the system is hydraulically well connected, it may be able to then recover fully following that, such that over the long run, the well does display the stability that we're looking for. So I'll pause there in case there are any questions, just because I think that was a major piece of interest.
I don't see any hands raised.
Okay, let's carry on then. This is another slide from the RAC 7 meeting, just an overview of the evaluation that's presented in the memo, some of the major pieces. Like I just said, the goal is to identify wells that represent stable, which we defined with both a correlation between that water level trend and precipitation record averaged between 2 and 10 years, as well as the long-term rate of decline being limited to 0.5 foot per year or less. After identifying those wells, the data were processed to remove the best fit linear trend so that even if there was a slow long-term decline up to 0.5 foot per year over the period of record, that trend was removed so that the well's water level record was would represent long-term stability, as well as could be reasonably done without, I would say, changing the nature of the signal. So that allowed us to include water levels that are influenced by a combination of precipitation and anthropogenic influence, and are not strictly 100% exactly stable in the long run. Maybe they do show some long-term decline that's very limited, but it's close enough to that the a significant portion of the, I would say that the record is substantially showing these fluctuations around stability, especially if you remove the long-term trend. After doing that, we also clustered wells that were similar, both in terms of location and properties, evaluated aquifer when we knew it, and the total decline value, the maximum decline over their period of record. Those wells that appeared to be substantially measuring the same water level signal were clustered and treated as a single well in order to reduce the spatial bias that is created by the fact that parts of the state are particularly useful for pumping groundwater, and we have high concentrations of wells in parts of the state. For the purposes of this analysis, characterizing statewide variability, we wanted to limit the bias imposed by that density of wells in particular areas by essentially collapsing the records of water levels measured from wells that are substantially similar and treating them as one well. After doing that, for each of those wells or clusters of wells, we were able to evaluate some attributes that were relevant for understanding the statewide variability in these characteristics that we use to define this dynamically stable range. That is the total decline from the highest previous measurement, as well as the rate of decline as measured using the form of the rate test. And I'll talk about that a little bit later. Identifying the rate in a way that's consistent with how it will be identified according to the proposed definition of reasonably stable. So those values were identified for each year in the record, and then along those records, maximum values were taken for each well, and those were defined as the characteristic values for the well. And finally, we also measured the percent of that period of record that the total decline and the rate of decline would have been less than particular thresholds. And we'll say more about that later. So, seeing no questions, I'm going to carry on to describing this detrending. There were a couple of questions about how this works. So here we see 4 wells, 4 hydrographs, and in each one, there are 3 lines. The black line with the stars is the detrended water level that was used in this analysis, and the purple lines are the ones that were used to generate that from the raw data. The solid purple line and the right-hand axis is the elevation of the water levels, these annual high water levels in each of these wells. The dashed purple line then is the least squares best fit trend line for those data. And the black line that we get is the result of subtracting the best fit line from the raw data. And that's the process of detrending. So for these wells, you can see the influence of detrending was pretty minor. And that's in large part because the long-term rate of change over the period of record in each of them was magnitude of 0.1 foot per year, plus or minus. We can also look at some examples with faster rates of decline, up to 0.5 foot per year in the bottom right. And the result is in each case shown in the black detrended water level to show how removing this trend gives a better indication of stability. And I think the most extreme, or the case where this has the largest influence is in the top right with Lake 4437, where the trend is 0.3 feet per year. That's still relatively mild, but the variability on top of that trend is also relatively mild, so that removing the trend has a relatively larger influence on that record. And I would say makes it more appropriate for understanding what the variability around the trend looks like. So after having done that detrending, we look at the examples of wells that were, again, presented in Rack 7, Deschutes 3016, and the values that were evaluated over the periods of record. For this one, the black water level trend is compared with the blue dashed line on the right side y-axis for precipitation. The correlation for this well is 0.22 when the precipitation is averaged over 6 years. And the resulting total decline that we measure is just under 21 feet and 0.3 feet per year. a couple more examples we already looked at. And now I want to talk for a minute about the clustering. So for many of the wells that were observed, the water level trends are somewhat similar. And wells are also nearby and at least plausibly consistent in terms of their selected aquifer and aquifer system. The criteria that were used for that clustering were that the wells should be within 10 miles, or if either well is known to be a basalt well, then 25 miles because they have larger hydraulic diffusivity. The water levels, the total decline from any measurement or from any measurement to its previous high measurement. So the largest water level decline as would be measured using the total decline test in the proposed definition, that had to be within 30% of the mean value between the pairs. And the aquifers had to be potentially the same aquifer. So if neither well had an aquifer selected in the department's groundwater information system, then they are eligible to be clustered, collapsed treated as a single well. If both wells have been identified as a particular aquifer or aquifer system, then they're only allowed to match if they're identified as the same aquifer or aquifer system. So if there is a clear mismatch, then they are disallowed from being clustered together. But if either of the wells doesn't have an aquifer selected, which is true for the majority of wells in our database, then they are eligible to be clustered if their behavior is similar from the perspective of the evaluation that was performed here. So there was a question about, doesn't that mean that there's a potential that we're over clustering, that we're in fact pairing two wells that are in fact in different aquifers? Yes, that is possible in this analysis. You could have two wells that are in different aquifers. They would only be clustered together for this analysis if they functionally provided similar data for the purposes of this analysis and were nearby. So looking at this hydrograph, we see 3 wells in Josephine County with the dots, and then the blue line without dots is the average precipitation record. And here we're looking at the raw data, so that's why you see a long-term declining trend in especially Josephine 3175. But for the wells in this cluster, the total declines in each of these wells were 8.1, 10.1, and 12.8 feet. So they were close enough to each other that they are substantially the same, and the cluster's characteristic value is taken as the average of those 10.3 feet. And then that was treated as if it was one well for the purposes of the rest of the analysis. And these wells happen to all have already been selected as in the Grants Pass Pluton aquifer. So they passed the aquifer test, but others were potentially eligible for clustering even if they didn't have an aquifer selected. Okay, so that's background on the
We have
basics.
one question from
Yeah.
Robin. Yeah, I don't want to make sure you saw that.
Yeah, hey Ben, just wondering if you dug into the like total completed depths or anything to try to fine tune whether or not they would be similar aquifers, or we're just relying on the water levels?
Just relying on the water levels.
Okay.
Yeah, completed depth is hard because especially in areas with steep terrain, you might have different wells that have different depths, but in fact access the same aquifer. So
Okay.
it's quite possible that that could be useful, and it certainly could be worth additional looking, but it wasn't immediately clear as a slam dunk to me is the right way to do this. But thank you for the suggestion.
Yep.
We also have a question from Greg.
Yeah, just looking at those, first of all, I guess I just want to clarify. So you are clustering those 3 wells together, is that correct?
Yes.
All right. Well, I mean, just visually looking at those, I mean, I can see that there's a pretty apparent downward trend in the the blue well, which would be, I guess, 3175. But the other two, just visually, I don't see a downward trend in those. And you're saying that your statistical analysis is telling you that you've got overall declines in those 2 wells.
No.
Okay.
The statistical analysis is something that's applied after detrending, after removing the long-term trend. So for the purposes of the statistical analysis, we would first remove long-term trends from all 3 of these wells.
Yeah, but I think you
Then,
mentioned that they had similar, maybe overall declines. Yeah, I think that's where I'm it's not quite clear to me, because I mean, when you say overall decline, that they're similar, and I guess I don't see it visually. They don't look like they're similar to me.
thank you. Now I understand the question better. I really appreciate that, Greg. Yes, and I can see how my language also would be confusing in that, because from one perspective, I talk about long-term decline over the entire period of record, and that's what's removed with the detrending. And that's different from what was statistically characterized, which is what I'm calling the total decline, which I realize is a very similar term, but I've distinguished them in my mind. The total decline in each of these cases is what would be tested with the total decline test in each year where the proposed definition of reasonably stable groundwater levels would be evaluated. So for simplicity, I'm going to go back a slide. Maybe we'll look at this one. In this one, you maybe look at the lowest measurement in 1993. The total decline for that year is the difference between that water level and the previous highest water level. So that in that case, it would be about 25 feet. That's different from the rate of decline over the entire period of record that was removed during the initial detrending process. And this analysis looks to characterize a total decline in each year for the period of record. So for each of these star water level measurements, it looks at the previous highest measurement and asks what's the drop in water levels between those two. So you get a time series of water level declines, and it also characterizes the largest decline for each well. So in this case, it would be from that 1993 measurement of about 25 feet. So this well's total decline for the purposes of the statistical analysis is 25 feet. Whereas the rate of decline over the period of record that was removed before even looking at this by the detrending analysis, I guess you can actually see it as we had the example here. The overall trend in this record, caused in part by that significant drop, is actually an increase of 0.1 feet per year. And we can debate about whether that's a reasonable approach. And there certainly are improvements that could be made for identifying the appropriate long-term trend in some records. But I really appreciate your question for helping distinguish this long-term rate of change, the one in purple, from the total decline, which is for each year, what was the drop to that year from the previous highest measurement. Does that distinction make sense?
I understand the distinction. I guess I'm a little concerned about how you're going to be using that overall decline, especially, maybe, I mean, how reliable are some of these, when you've got, when you're looking at SHER 340, for example, and you've got, a couple of measurements that fall way below all the other measurements, I guess you have to have some question or concern about whether those are outliers. Were those accurate measurements? Were they the same time of year? Those kinds of things. So, I guess I'm still not, it's not clear to me how you're going to be using the information, from those calculated overall declines in the the ultimate analysis.
Thank you. Stay tuned. That's the very next section. And while we didn't end up including any outlier rejection techniques in this analysis, we did, especially for the wells whose maximum declines were especially large, all those that were over about 20 feet, we did actually look at the records and the individual water level measurements that were the basis for measuring those declines, just because had the same concern, like, are these measurements reliable? Is it possible that these are just flukes of various flavors? And for all, I think that we identified one well that had whose water level trend was influenced by a deepening construction behavior in that well, and we decided that it shouldn't be treated as measuring the same aquifer over a long period of time. But with the exception of that one well, none of these measurements were found to be suspect. They all had confirmatory measurements from, earlier in the year, later in the year, multiple years before and after. We don't have, aside from the apparently distinct behavior for which there could be a lot of explanations, we didn't have an obvious reason to exclude them, so didn't feel comfortable rejecting outliers from this analysis. There was another piece to that. And that influences the inclusion of those large water level drops. And I'll say most of the large drops are not flukes like this. Most of them are in wells like at the bottom right, Jack 3300, sort of consistent drops that I'd say are more characteristically measured over multiple cycles of water level fluctuations. But the fact that we included some of these that are, say, less consistent, does influence the eventual distribution of total declines that were evaluated among these wells. So we'll see that in the next section.
Okay, appreciate that, Ben. I do have one more question about the last slide that you showed, where you were showing the 3 clustered wells.
Oh, this one, yeah.
Yeah, I mean, just looking at that, I guess I would not expect that the well represented by the blue line would be in the same aquifer as the other 2 wells. So can you explain how you made that determination?
I did not. I think in all these cases, the aquifer was determined by other groundwater section staff. We have a schema in our database for determining aquifer systems. We have 7 aquifer systems around the state and hundreds of aquifers within those. And groundwater staff are trained and empowered to select those when they are operating in a portion of the state. So this was determined by a staff person who was working in this part of the state, had looked at the water level data in this well, probably had visited this well. I don't remember off the top of my head the entire history of that. But the aquifer determinations were not mine. Justin?
Yeah, thanks. I'll also point out that the the second x-axis here is groundwater depth, not elevation. So this could simply be a well that's, 20 feet higher on the hill that's accessing the same aquifer.
Oh, yeah.
Oh, no, I'm looking at the trend. I'm looking at the.
Okay,
trends.
well, yeah, all right. I think you've answered the question though. Thank you.
Okay, thanks all for the questions. Carrying on then, let's look at the results of the total decline test, like we just started talking about. So this is reviewing stuff we've essentially talked about, but I want to reiterate that the department has, for the moment, abstracted the value, the limit on total declines from 25 feet to a variable because we are awaiting review by the U.S. Geological Survey on this analysis. And we're taking feedback from them as well as from the RAC and wanted to leave room in case that that review led us to update this and find different values. We are trying to let this process be driven by the best available science, which is peer reviewed, and we appreciate your involvement. The department has proposed measuring declines from the pre-development level, and this is still in discussion, so not final. Stay tuned for RAC 8 to hear what we actually go with, but for the purposes of this analysis, the total decline is measured in each year is measured relative to the previous highest water level measurement. So imagine that in a given year, you're only looking at the record leading up to that year. What's the highest known before that measurement is how the total decline test was run for the purposes of this analysis. And I think that's appropriate. The reason why we did that is because there are cases where the first water level measurement might be nowhere near the top of this dynamically stable range. So here in Deschutes 3016, the first measurement is pretty close to the center of this range of water level fluctuations. And if the goal is to use this total decline allowed magnitude as the height of the dynamically stable range, this blue bar here, what we want to be measuring is relative to the highest measured water level in a record rather than the first. So applying the test as described to each of the water levels in these wells that were selected for this analysis, and then taking the largest decline within each well, we could look at a distribution of those largest declines, maximum declines, around the state. So the x-axis here is the largest decline per well or cluster of wells between 0 and 40 feet. And the y-axis is the percent of those clusters of wells, which a cluster could include just one well, whose maximum decline is less than the value in X. So for small values of decline, there are essentially no clusters whose maximum decline is less than that. But as you have a more generous tolerance, you capture a larger percent of the well clusters from this analysis within that threshold. And for example, if you look at the 90th percentile, below which 90% of the well clusters in this analysis have their maximum decline, that level is just about 24 feet. We can then look at how these values are distributed around the state. And here the color scale is set up to highlight values that are more than 25 feet or 25 feet or greater are in warm colors, pink, orange, red, I guess yellow, orange, red. And at least the color scale is hopefully better here than it was with the projector at the RAC meeting. Blue values are, green and blue are below 25 feet. And you can see that the values above 25 feet are scattered around the state in different basins. And this is part of why the department is the fact that you see a reasonably wide distribution of total declines among these well clusters in most of the basins. And granted, there are issues here with limited number of clusters within each basin, but qualitatively, the similarity in distributions across the basins is part of why the department is proposing to set these thresholds statewide. The other perspective, oh yeah, Greg?
Yeah, just a point of clarification for me. Does each one of those dots represent a cluster of wells then, more than one well?
It represents a cluster, and a cluster can be only one well.
Okay. Okay, so some of those dots are more than one well, some are just single wells.
Yeah, and I think that there's even a map in the draft memo, which is, with apologies, not yet actually converted into this nice Oregon Lambert projection. It's just a latitude longitude scatter plot of the well clusters colored by the number of wells within them. So you can see that how those multi-well clusters are distributed. They show up in the places you would expect, the center of the Willamette Valley, around Klamath Falls, around Bend, like.
Yeah. Okay, thanks.
We have a question from Tammy in the chat. I don't know if you can see the chat, Ben, or if you need me to read it. Or
Please.
Tammy, if you want to come on and ask your question.
Sure, I can actually ask the question. And I think I know the answer, but I just want to make sure that I understand. So all of these analyses that you're doing now from here and subsequently, we're still working with the same set of wells that you identified in the beginning with your precip test, you know, the correlation of precip and with the less than 5.5 feet per year, correct?
Exactly.
And just to, because I'm not familiar with the database really, how many wells is that out of what total? Just round numbers, you know.
We have about 30,000 wells in the groundwater database. About 10,000 of those have multiple annual high measurements that are indicated as likely near static. And of those 10,000, I think about, I don't remember, it's about 230 or 240 wells were included in this analysis, and they clustered down to a little over 100. I'm sorry, I should know that off the top of my head, but it's been a couple weeks.
No, that's good enough. You know, I just want an order of magnitude kind of.
Yeah.
And sorry, Ben, real quick, just to describe why we went from 10,000 to 200. Can you describe duration of record that we were looking at too, to make sure that we had an appropriately long record to look at?
Thank you. Good point. And yeah, in order to get a sense that we were likely looking at records that actually are stable, we wanted to test that 1/2 foot per year of decline over a significant period of time, as well as to make sure that we were getting a robust correlation between the water level behavior and the precipitation record. We imposed a limitation that the water level record had to have at least 25 annual high measurements. So it had to span at least 24 years. Most of them span, 25 to 30 years. There are quite a few that have over 50 years in their record. But the requirement for the minimum number of measurements helped ensure both that we were getting the meaningful correlation and a real test of the long-term stability, which is the real, in my mind, the most important question for including wells in this analysis. There is also a sensitivity analysis presented in the memo of how the results depend on that 25 water level minimum.
Oh. Okay, thanks.
Great, excellent questions. So this figure is one way of looking at the results, statistically characterizing these total declines, which is what's the maximum value in each well's period of record. There's another way to do that, which is asking what percent of time does the water level remain, what percent of the years is the total decline less than some value? So if we instead use that metric, the blue line here considers all the well clusters. And the curve has a similar characteristic as a cumulative distribution, again, with total decline on the x-axis, slightly different scale. It's 55 feet instead of 40. But the curve rises more quickly towards 100 because the percent of time that a well has total declines below some threshold is by definition greater than the percent of wells who are always below that threshold. So if you were to, for example, take 25 feet with this vertical dashed line, that corresponds to 99% of the time on average that these well clusters have total declines less than 25 feet. Only 1% of the time on average do well clusters in this analysis exceed 25 feet, even though, looking at this one, 10% of the wells do exceed 25 feet at some point with their maximum value. So this is understanding maybe how representative those maximum values are of the rest of the record over a whole. But the department still is looking at this analysis because the question does matter whether water level fluctuations do exceed a given amount, because that causes the determination of reasonably stable to switch from reasonably stable to not. And if you're in a well that we are otherwise saying should probably be considered reasonably stable, that's an outcome we'd like to avoid. We don't want to. We want to design this proposed definition with consistency in mind as one of the objectives, balanced again against the desire for sensitivity. But using the maximum value like this is one way to evaluate consistency. It's not the only way, but that's why we've been looking at that. But even among the clusters that do at some point exceed 25 feet, that's this orange line, those have an average percent of time that they are below some threshold. And I think it's 86% of the time that those remain under 25 feet, looking at their entire period of record. The other piece of the analysis that I did want to bring up, because there were a couple of questions about it, is I think addressing this question of looking for stable versus natural variability. Again, there is a sensitivity analysis presented in the memo of how the total declines vary with respect to the minimum correlation imposed. So as you increase the x-axis, a minimum r squared, You have the bottom graph shows that you have fewer wells that meet that criteria that are sufficiently correlated, but you also are getting maybe a more representative sample of correlation, or that's the wrong way to put it. You are requiring a more significant correlation among the wells selected with precipitation. And the results fluctuate, roughly between maybe 20 and 30 feet in the range of 0 to 0.5. The selected value of 0.2 was both appropriate because it corresponded with a well that we know to be strongly driven by precipitation, and we were confident we wanted to have included in this set. But the results don't change by an order of magnitude, even if you were to fully relax the requirement of correlation to precipitation, or to significantly increase it beyond the value that was included in this analysis. So, carrying on. Now let's look at the rate test. There were some good questions about how the rate test works, and I just want to review the mechanism because it's easy to get confused between what was done with the rate test versus what was done with the analysis. And I want to explain how those are consistent. So let's look at an example well here, LAC 6388. This is the raw record, and the colors on the shaded background indicate the determinations of reasonably stable or not, according to the definition, I think, proposed in RAC 6. The gray area at the start is insufficient data because you don't have enough measurements to evaluate the rate test. The first couple of years occur during this period of declining water levels, and that rate test indicates that the rate is steeper than half a foot per year. So that it's classified as not reasonably stable according to the RAC 6 definition. Following recovery, you're able to see water levels become reasonably stable again. So how does this work if you look at a couple of particular years? For that early, those early measurements during the declining period, the only measurements you're able to compare against in the past are those that are at least 5 years ago. So 1, 2, 3, 4, 5. You get 2 measurements going back, and the rate, the slope here in the orange line, for all those measurements is steeper than the reference here on the right side, half a foot per year. And this approach is demonstrating estimating of the rate using the endpoints of a period of record, which is a legitimate way to do it. It's not the only record. Things like the send slope are more robust, but I think that it's useful for illustrative purposes. If we look at a later measurement, which is even deeper than this early measurement that was not reasonably stable, we can compare it against the eligible previous measurements and color those slopes by whether they're steeper in orange or shallower in blue, compared with that 0.5 feet per year, which again has been proposed in RAC 6, is not set in stone at this point. But what we can see is that for this measurement, there are indeed water levels in that range of 5 years in the past, with this first, I guess, second vertical dashed line behind that measurement. The first few of those are steeper than half a foot per year, but as you have a longer period of record to average over, a more full accounting of the cycle displayed in this well, and also averaging those declines over a longer period of time, you're also able to estimate rates of decline that are slower than half a foot per year, going back up to 20 years, the second vertical dashed line. So the rate test looks at all of these rates between 5 and 20 years and takes the shallowest among them and says this is the rate for that particular year. In this case, it looks like 2005. So 2005's rate is a number, I don't think I wrote it down, but it's certainly shallower, that maybe it's 0.2 feet per year or so. And you can repeat this exercise for every single year, looking at that window of historic water levels going back 5 to 20 years. I'll pause there in case there were more questions on that.
I don't see any.
Still going to take a drink.
We'll allow it.
So I'll ask a question then. Can I just jump in?
Please.
Sure.
So I understand how you're choosing the minimum for each year, how you would step through each year then and ask the same question, right? And then maybe you're going to show this next, I don't know, but so then you would have this collection of numbers, one number paired with each year, representing the minimum of the slopes. And then in your description, you said you take the maximum of those. Is that okay?
Spot on.
Got it. Okay.
We got Greg as well with his hand up.
Yeah, I guess just for clarification again, all these measurements that you're looking at, they're all from roughly the same time of year, like the same month in the year.
The annual high water level for the purposes of this analysis is the highest measurement made in each well between the months of January and April inclusive.
Yes.
And previous analyses we've done have suggested that that's generally a good way to identify annual highs, that it's generally consistent. Most wells are measured once per year in March or so. There's some variability. And it's true that if you measure a well in March one year and April another year and February a different year, you might have an impact of that shifting measurement on the water level behavior. And I haven't attempted to evaluate or correct for that in this analysis.
Well, yeah, because the later you get into the season, the more you're going to be under influence of other pumping wells, nearby.
For sure. Something that a couple RAC members asked was about annual high water level measurements and what level of review they've got. And there are a couple of things to say about that. One is that water levels are included from a variety of sources here. These could be measured by WRD staff, by the USGS, by certified water right examiners, or others submitting water levels for the purposes of the permit condition static water level program. The WRD and GS follow the USGS protocol for measuring water levels, which includes sticking around, taking multiple measurements to check that they are agreeing with one another well enough to call it static. We're working with CWREs to institute a consistent protocol for them, so that they're measuring water levels in the same way that department staff are, but we don't have the same level of control over that. So we can hope that for the majority of these measurements, if they are reported as static, someone has waited around and checked that the water level is not actively coming up by a couple hundredths of a foot per minute, which would be indication of recent very nearby pumping. It's obviously a matter of degree. how one defines what is static, because groundwater levels are always changing and recovering from pumping on some time scale in most aquifers. But the water level measurements that are collected by WRD staff are not going to be heavily influenced by, significant nearby pumping that's actively recovering quickly. The other possibility is that water levels do get manual review by groundwater staff as they have time. So if there is a measurement that is hundreds or even tens of feet below previous measurements, groundwater staff can look at that and evaluate whether it's plausible given groundwater, given our understanding of the hydrogeologic system. That review wasn't generally done for this analysis in particular, but it's an ongoing process that groundwater staff go through. Justin?
Yeah, I just want to make sure that I jump in and sum up to say we're trying, like, we've made a number of assumptions and decisions, right, in applying this, and we're trying to balance what's an appropriate set of data to do this analysis on, and we want to acknowledge it's not perfect, but appropriate for the purpose. So, I mean, we could shrink it down to just March water levels, just by X number of people, just by what have you. That's all in the database, but then we really shrink down the amount of available data and what we're going to require when we actually potentially do a review under these rules, right? We want to ensure that we're looking at the data we think is appropriate to make decisions going forward, and to be clear about what data we're going to use and how we've made those choices. So that should all be detailed out in the presentation, and so that's, I guess what I'm trying to get at is, sure, you can have a little bit of interannual variability, but the question is, do you think it's significant enough that it will affect the outcome when applied? And do you think that that is significant enough, balancing against having sufficient data to make, an assessment? So, we'll stop there. Thank you.
Thanks. So there's one other piece of this analysis that I wanted to go through to distinguish how the rule operates as proposed from how this analysis was conducted, which is thinking about the period of record that is eligible for inclusion in the analysis. So in Oregon, these precipitation fluctuations are dominantly occurring on decadal timescales, and we see that in the vast majority of the examples in this analysis. And what that means is that oftentimes, if you happen to be measuring during a period of declining water levels for the first few years, that this proposed rate test isn't going to have a full decade of data to average over if you start evaluating reasonably stable after only 5 years. If you only have 5 years of data and you start looking back, you might be only looking at the declining limb of one of these cycles. And that is an effect that we see in this well and a number of other wells in this analysis. And in an ideal world, or I'll put that differently, if the only goal was to get the best assessment of reasonably stable, given this decadal cycle of fluctuations, the rate test would require 10 years or more of data. And the department is balancing that objective of robust assessment against limiting the burden of data collection on applicants for water rights. So in the proposed definition, the rate test can be evaluated with only 5 years of data, or data spanning 5 years. For the purposes of this analysis, the rates are only eligible for being representative, characteristic for a well, inclusion in that maximum set that Tammy just asked about, if they have at least 10 years of data spanning before the year of interest. So in this particular case, those measurements in years 5, 6, 7, 8, and 9, to the left of this vertical dashed black line, the rates here in the purple and on the right y-axis are much steeper, using the smallest best fit among that 5 to 20 year averaging period. Those decline rates are significantly steeper in these years compared with beyond, and these ones are excluded from the analysis of the rates for the purposes of characterizing the rates in these long-term stable wells, because we're designing the limits around how the rate test is intended to operate. That is, when it has a full decade of data to average over, so that you are able to not just be restricted to a falling limb of one of these precipitation correlated cycles.
We have a question from Tammy before you
Yeah,
move
Tammy.
on.
Hi, yeah, so before we move on here, because I think, I just want to make sure what I'm looking at, because I think this answers one of the questions that I had in a slightly different graphical way, but you have on the right-hand axis, you have this defined as the annual rate of decline in feet per year, which in my head, I would think of as in any given year, you know, what's the difference between this year and the previous year? Okay, but I think that's not what that is, right? This is the result of your rate test, right?
Yes.
And then the maximum, the way you're applying this, if we get rid of the first 5 data points or whatever, the maximum would be, say, in 1970, 1, 2, 3, 4. It looks like 19. What I can't 78 or 79, right? And it would be at 0.2, around 0.2 per year. Okay, I think I get it. Thank you.
Exactly. Thank you. You're absolutely right. I should have labeled the right axis as rate test rate or something like that. And the only reason I call it annual is because I wanted to distinguish the annual rate from the characteristic rate, the maximum rate among all of those annual rate test rates.
Yeah, it's because
For
there's a value for each year. I get that, but it's not limited to that year. So yeah, okay.
Exactly. Thank you. So yeah, here's another example of a well where that during that early period you would have higher rates, you know, about half a foot per year, but excluding that period by requiring at least 10 years of data for the rate test to operate as designed, the maximum characteristic rate for this well becomes 0.3 feet instead of 0.5. And in the interest of time, I'll just say you can look at the memo about how the results vary depending on the minimum initial span required for this. And there's some discussion of that, but I want to leave some more time to get through the slides and the other discussion. Talk more if others are interested. This is again a slide presented previously, the analog to the results. These are characteristic, so maximum rate over that eligible period in each well or cluster of wells on the x-axis, and the y-axis is the percent of those well clusters being passed in all years. And the 90th percentile here is between 0.6 and 0.7 feet per year. And for comparison for reference, the Mann-Kendall test with significance of 0.05, that doesn't have this maximum allowed water level decline rate as a parameter. It instead just takes the results over the available data leading up to a given year, and that one is more sensitive. It tends to find declines in more of the wells, so the percentage of wells that have rates less than that in a given than a given threshold is smaller. Or I should say that differently. The percentage of wells doesn't depend on the threshold. The percentage of wells is smaller than what you would get if you used 0.5 or 0.7 feet per year in the proposed rate test. And just as we looked at before, you can look at both the maximum values in each of these wells. You can also look at the percentage of time that the rates, the annual rate tests rates, annually varying rate test rates, the percentage of times that those are declining less quickly than a given rate threshold. And as with the total decline test, the rates are also higher, the percentage of wells that pass those at a given rate is also higher than if you look at the percentage of wells. I think I said that wrong. The percentage of time is higher than the percentage of wells that pass all the time for both all the wells in blue as well as for the wells that fail at some point, as in one of their years or more exceed a given threshold. But we discussed that in RAC 7, and the same summary from RAC 7. Here we go. That number that you were asking about earlier, 234 wells included in this analysis. These wells are ones that were found to be long-term stable, so that over their period of record, the rate of decline is less than half a foot per year. The results didn't show consistent variability by basin, which is why the department's proposing a statewide thresholds, and you can determine thresholds based on saying we want to include 90% of these well clusters. You can also think about the percentage of time within each of those well clusters that the record would remain stable at a given threshold value. And we are really appreciating all of the feedback from the RAC today, tomorrow, last week, all of the submitted comments and the rest of the discussion we have today. And we're also still anticipating peer review from the U.S. Geological Survey on this work. So with that, thank you.
Okay, we have a question from Tammy. So, and then we're gonna, I guess, let's take questions from the RAC first, and then we'll ask for questions from the public. Again, please limit comments and questions to the content presented today. Thanks. Go ahead, Tammy.
Okay, so if you go back to like slide 27, I just want to propose a way of interpreting this, and you tell me if I'm right or wrong. So it seems to me that, you've got a null hypothesis here with this group of wells, that they are in fact stable, reasonably stable. And so, you've shown here quite clearly, and in the memo that you created, you had more than one choice of percentages that you could allow. So basically what you're doing is you're prioritizing here what would be called a type 1 error. So you don't want to reject the hypothesis that the well is stable if it is indeed has been identified as stable. And you know, we could choose a percentage, you know, of wells that might fail the test and accept, you know, but that has all sorts of implications that you talked about, right? So you want to make that a low possibility. But it seems to me that there's the type 2 error, right? Which is that you would actually assign reasonable stability to a well that in fact isn't reasonably stable. And you haven't shown us what the probability of that is. Would you agree with that? And so you could, I mean, maybe it's obvious, it's not obvious to me, okay, but you could identify a cluster of, or not a cluster, don't want to, you know, a subset of wells, you know, similarly, and I don't have problems, just by the way, I don't have like problems with your methodology here. So if you were to identify like a subset of wells in the same order of magnitude, like, you know, somehow that you know should fail the test, right? And you were to do the same sort of analysis here, how, you know, how often would the wells fail the test? You see what I'm saying?
I agree, and that's a good idea. Yeah, we could do that. It would we would need to decide a way to identify the list, the set of clearly
Right.
declining trends, but that may be possible. I think that could be done.
Okay. I think it's a good idea too.
Okay, are there any other RAC members with questions? I see Greg's got his hand up, so we'll go to Greg.
Yeah, I think, you know, maybe this is this is a pretty fundamental question, but keeps kind of popping up in my mind, and that is, you know, you've got this rate test, or this not the rate test, but I mean this overall decline that you're looking at. And I guess I can't help but wonder why we're even concerned about that if water levels appear to be otherwise stable. I mean, so why does it matter whether it's 25 feet or 40 feet if water levels, you know, if we're still, everything is still fluctuating within this, you know, dynamically stable range, whether it's 25 feet or 40 feet or 5 feet? I mean, why does that matter?
Good question. I think what we're aiming to do is understand the dynamically stable range, or the range of dynamically stable ranges that we might observe statewide,
Okay.
and characterize those so that we can set a statewide rule and evaluate reasonably stable in a way that meets all the other objectives for the proposed definition. So for the sake of understanding declines, it's important to have at least if we are using a rate test as proposed, then you also need a total decline test in order to detect long, slow-term declines. And if you're going to have that, then you need a way to decide what the threshold is. And this is the department's approach to identify that threshold. And the key is that we're using a broad set of data in wells around the state, and acknowledging that there will be some of these type 1 errors, as Tammy described, some of the wells whose fluctuations are greater than whatever the proposed threshold ends up being. And they will occasionally end up being characterized as not reasonably stable, and that's a problem. This analysis shows that even those that exceed that threshold tend to spend most of their time not in this not reasonably stable regime. but I just lost the train of thought. What is not presented here is the other side of the story, which is the errors of declines that are not detected because of particular thresholds, as Tammy just described, or analysis that's presented in a separate memo, piece of work for understanding some of the impacts of those declines that occur. So I'll pause there.
Okay. Let's we'll pause on the RAC questions. I don't know if there's any other RAC members that have questions, but we'll come back to you. I just wanted to give members of the public an opportunity to comment or ask questions, again, focused on the material presented today. I see Owen has his hand raised, so I'll call on Owen first. If there are other members of the public who have joined us that wish to ask a question or comment, please raise your hand. So go ahead, Owen.
Yeah, I just wanted to go back to the sort of the 0.5 foot per year and the 2 to 11 year window. And I guess I just wanted to understand in the context of this analysis, how was did the 0.5 foot per year decline rate, it sounds like that's just coming from RAC 6, or was it part of the purpose of this exercise to identify that? And then kind of the same question for the 2 through 11 year window. Did that come from the analysis of the data, or was that something that the department kind of imposed as part of the analysis?
Those were both parameters imposed on this analysis that, based on professional judgment, captured the intent.
So just in terms of thinking, because there's these citations to Gleason and Cuthbert in this memo and in other RAC materials, if I'm understanding correctly, that this T sub H that's described in those papers, which is sort of the human timescale, what they define as being the human timescale for dynamic stability, the department has made the judgment that the human timescale that's appropriate for dynamic stability is 2 through 11 years. Is that an accurate characterization of that, how that judgment is being applied as part of this analysis?
I don't think so.
Yeah, I agree. I don't think that. So again, just to make sure we're framing this right, we're trying to come up with a quantitative rule set that can be applied to data to predict the future, right? So we want to take available data that's in the vicinity of a new application and use that to assess, are water levels reasonably stable? And just to be clear, like, we did a qualitative assessment long before RAC 2 back in May, right? And we came up with these values, and those were values just hydrogeologists looking at hydrographs and saying, here's something that's, we'd call dynamically stable and it's about in this range. And we're doing this quantitative analysis because, in response to a bunch of questions we had, and to make sure that we can quantify that our proposed rules are reasonable based on looking into the past. And so we're imposing these timescales and this range on backward-looking data in our analysis. And I think the 2 to 10 is more of like, what's the timescale of, water level response to our decadal climate cycles, rather than what's the forward-looking timescale that's a human planning timescale. Does that make sense? Or does that answer your question?
Maybe I'll rewatch the recording later to see if I understand it.
Fair enough. And Ben, did you have anything to add to that? Did I do a fair job of describing that?
Yeah, I mean, I think I would just add that the 2 to 10 windows is the timescale for the moving window average. So it's not like we only are looking back 10 years. The point is that that's the type of relationship between precipitation and groundwater level fluctuations that we're looking for. And it's possible that there are longer term fluctuation or relationships between those fluctuations that also would be of interest. Whether those could be appropriately captured with the available data from the perspective of this analysis is something I'd want to think about more. But I appreciate the question.
Okay, before we go to you, Greg, I just want to check and make sure, is there anybody else joining as a member of the public that has a question or comment?
I think that's Malia for public comment.
Yeah, it's
Oh, okay.
for
All
public
right.
comment. We're sharing.
Your
one
team.
stack.
We're doing a tag team.
We're
here.
doing a tag team. We changed.
I got you. Okay, Malia,
Okay.
go for it.
So could we go back to the slide that was showing the hydrograph for CLAC 6388 where you were talking about the rates? Okay. Yeah, okay, I looked up the hydrograph real quick, and that low number there on the left where you've excluded the data, those low points, that water level was measured in October of 1967. So these hydrographs that we're looking at,
I don't think it was.
yeah, I think it is. Cause see, there's crap. Okay. Yeah, because there's 1970 right there. So 67 would plot there. So I guess the point I'm trying to make is you're looking at the total water level record on file.
I don't know, Malia. See, this is like over 75 feet here, feet below land surface.
That's what it was.
That's about 66
feet. Okay, well,
So
I don't know. I guess that was why we had the question of, it looks to me like, and you can clarify this, that you're including all the water levels measured at a well and matching that to the precipitation. So if we have to show maximum seasonal variability. So we do have wells with water levels not only measured at the seasonal high or thereabouts, but we also have water levels in some of these wells measured at the seasonal lows. Is that true?
I don't think that's correct. I'm looking at the hydrograph for CLAC 6388 here, and I think you're pointing at this October measurement here.
Yeah.
That's true. That's down at 75.5 feet of depth, as you can see from the pop-up. But the deepest measurement we have here is 66 point something.
Okay.
We're not looking at October measurements for this analysis. We're looking at annual highs between January and April inclusive.
Okay. All right. That answers that question. Thank you.
Thank you.
what about my question about how about a systematic approach? Okay.
Oh, and one more, Greg, you change.
Yeah, I'm sorry.
You change.
I probably should have asked this question before, but I guess, and maybe this isn't the right place to do this because it's not really directly applicable to the analysis here. But the question in my mind is that, you know, when we finally established how we're going to do this, and you're going to be, you know, doing reviews for new applications, are you going to have some kind of systematic approach to evaluating correlation between water level data and precipitation data so that you can, you know, so that you can avoid, I guess, making a determination that water levels are declining when the real reason may be because, you know, we've had several years of below average precipitation? No.
The point of this definition is to create an objective definition that can be evaluated without needing a hydrogeologist's subjective interpretation. It's trying to create some uncertainty in the context of limited information. So, excuse me, trying to create some certainty in the context of limited information so that we can be consistent in our evaluations. I could imagine a really great definition of reasonably stable that does account for precipitation, and the definition would immediately become quite complex to the point that it would sort of be in strong tension with the department's other objective to retain this definition as simple and something that can be written into rule and evaluated objectively.
Yeah, and I'll jump in to add, this kind of gets to some discussion we had during the RAC process where I believe it was Tammy or others asking about, are we taking potential future climate variability or climate change into account? And the answer is we're not. We're really setting up these rules based on, you know, our assessment of the past, and water level decline of more than half a foot a year or more than 25 feet could occur due to, you know, pumping or due to climate change. But from the perspective of these rules, regardless, we're going to assume, like, once those thresholds are tripped as we have them set up, we're going to assume that that's going to persist, and, you know, unless until proven otherwise. So, you know, if the future holds more variability than the past, we might have to revisit these rules, but we are consciously making the choice not to try and guess at that right now.
Okay, I wasn't asking you about guessing, or I wasn't implying that you would. I was just, the question was, you know, is there any way to sort of systematically analyze that?
Well,
because I guess my concern is that, you know, we could have 5 to 7 years of you know, below annual precipitation that could be the main cause of a well showing you know, declines that exceed the threshold.
yep, but
So,
we've looked at that in the past, right? Like if we've seen dry spells in the past in our 25-year record chunks that we're looking at, then that will be included in the natural variability.
okay, so what you're saying is the methodology that you're developing now it attempts to sort of account for that.
Yeah.
Okay. All right.
Tammy, did you have a response?
Yeah, I was just, you know, thinking, so it's not clear in your write-up which is the more restrictive requirement, right? Because you're imposing both the long-term record length over a minimum of 25 years, half a foot per year. That's one threshold you're applying, right? And then you're applying this R squared of 0.2 with precipitation. I can't remember in which order this was done, but one of them is going to be more restrictive than the other. And, you know, it seems to me that the correlation with precip is almost superfluous. You know, you could, like, which is the bigger filter here? You know, the long-term half a foot per year or the R squared of 0.2, which, you know, you showed in sensitivity analysis. I mean, first of all, that's not a very high R squared with precipitation anyway, and you showed that it's not, the results aren't all that sensitive to it. So, you know, isn't that just a little bit of a almost a superfluous additional constraint, or no?
The correlation with precipitation doesn't have a like order of magnitude impact on the results. I don't think I would call it superfluous. I think that the correlation with precipitation helps us get a sample of variability that we do know we want to account for.
Okay.
Okay, Ben, can you go to the wrap-up slide and then we'll take Steve, unless you have a question about the slides. I'm going to go to you next. Steve, did you want to ask a question or make a comment?
Just real quick. I think the
Okay.
methodology here seems sound. Predictive power as you're looking at the future based on the past, reasonable statistics. But I do think Tammy's issue of the type 2 error is important that you answer that, because then that will help with some of these questions we've heard today. But the ability to identify that type 2 error, how big is that? And that will give you a good, strong issue in terms of your intent to predict the future based on the past. And that's my only comment.
Thank you.
Okay. Do any other RAC members have any questions? Want to be sensitive to the time and kind of wrap up here if we can. Don't see anything. Okay, so just a reminder, we're going to be presenting the same slides tomorrow, 9 to 10:30. You can join us again. You're not restricted to one or the other meeting. Same is true for members of the public. The agenda with the Zoom link is on our rulemaking website, which I dropped in the chat. We're asking for feedback on the materials presented today and the materials that, same materials, but presented tomorrow. For that input from RAC members, that we receive that by the end of the day tomorrow. I know that's a tight turnaround time, but we want to be able to take your input as well as what we're going to hear from USGS and make any, adjustments that we might, need as is appropriate prior to our next RAC meeting on January 23rd. So that's why the tight timeline there. As far as what I'm going to do is I'm going to get the PowerPoint emailed out to the RAC, so you have it. I'll do that today. These materials are going to go on the website, but I have to work with the web folks to get it up there. So it might take me, may not be able to get it all done today. I'm going to do my best, but and then also if somebody has a need to re-listen to the Zoom recording prior to me being able to get it up on our YouTube channel, I think once Zoom does its thing, I can email out the direct Zoom link as well if there's that sense of needing to, if you can't wait until I'm able to get it up on the website, I can send it to you directly. So there's a question from Robin in the chat about the timeline for the USGS review. I'm going to let Justin take that.
Yep, we're expecting that early this week, ideally tomorrow.
Okay, I think that's all we have. I want to thank everybody for this was a great discussion. Ben did an awesome job. So proud of you. I will probably see some of you tomorrow. So with that, I'm going to stop the recording and end the meeting.
Thank you, everybody, for your input and questions. Appreciate it.
Yeah, thank you.